All right, hello and welcome back to this ALEKS explanation video series. This is a ALEKS topic that's called calculating and using the Van Hoff factor for electrolytes. This was another requested video, so thank you very much for the requests. Feel free to keep those coming in. It's probably best if you just comment below. That's the way that I'm going to see it the quickest. So if you've got another video that you'd like me to make, feel free to leave a comment below. And thanks a lot. So for this topic, I'm going to go ahead and do two different instances of this. I'm going to talk through obviously all of the conceptual things that we normally do. You can see that I've laid out some of the annotated some of the information that we're going to need for this already. So just basic information. Glycine's got a molar mass of 75.07. Ammonium chloride's got a molar mass here. I've underlined this term Van Hoff factor. That represents this I value in this equation here. So I want to talk a little bit about what this represents, what this Van Hoff factor actually means in terms of, this problem or just sort of in general. So this is a colligative property type problem. And so colligative properties are things that are determined by the amount of solute that is dissolved in the liquid or, whatever. If it's frozen, then it will be in solid. But basically, they are properties that are determined by the amount of solute that is present. Now, some things, when they dissolve, they dissociate. They break into multiple pieces. So if you think about sodium chloride is going to be table salt, and when you dissolve it in water, you're going to get sodium plus ions and Cl minus ions floating around. So in that case, the Van Hoff factor sort of corrects or takes into account the fact that you're breaking something into multiple pieces. Whereas if I dissolve glycine or another sugar, basically any molecular compound, it's not going to dissociate, right? When you dissolve glycine, or if you dissolve another sugar, or urea is one that we're going to see, I think, it's not going to break up into constituent parts. It's just going to stay together as one piece. So in that case, the Van Hoff factor will be 1. So we don't really need to worry about it in this equation here, this colligative property freezing point depression equation. But if you've got an ionic compound like ammonium chloride, that Van Hoff factor might be something like 2 or 3, or it could also be something that's not a whole number. If it's not a whole number, what that would indicate is that it's partially dissociating. So if you're familiar with weak acids, we know that weak acids only dissociate a little bit. Same idea there. So this Van Hoff factor I is basically going to be a measure of how many pieces does that compound dissociate into when it gets dissolved in whatever solvent you're talking about. And again, it does not necessarily have to be a whole number. It does not have to be 2 or 3. It could be something in between, essentially. Okay, so let's go ahead and do this problem. In terms of the actual math that we're going to do, it's pretty straightforward, but obviously conceptually, that's where the challenge lies. In this problem, essentially what we're going to do is we're going to apply this equation twice. We're going to use this equation first to solve for the Kf for our unknown solvent X. So we've got this freezing point of pure X. That is our solvent. And this equation is really going to govern the behavior of our solvent. So that's the Kf, the freezing point depression constant for whatever solvent we're looking for. Delta Tf is the change in freezing point. So how much does the freezing point change? How much is it depressed when we add that solute in there? This funny looking M is molality. And molality, I've written out over here, the units for that is moles of solute divided by kilograms of solvent. So we really have to be very careful here. When we're doing these colligative property type problems, we use molality. And the reason for that, I don't really know. That's just sort of how it's been done, how these equations were originally established. I think it does make sense because we're sort of treating the solute and the solvent separately. But in any case, that's what we need to use. So let's go ahead and jump into this. For the first part, basically we're given information for when we dissolve glycine into 1.2 kilograms or 1,200 grams of this mystery liquid X. We're given that the freezing point is lowered by 7.3. So basically as I'm reading this, I'm sort of picking out, I'm saying, okay, well, this is delta Tf. I can use this information here to solve for the molality. The Van Hoff factor I for glycine is going to be 1, and I know that because this is a molecular compound. This is not an ionic compound. I only have non-metals up here, C2H5NO2, things in the top right of the periodic table. So my Van Hoff factor for this, based off of that solute is going to be 1. So let's go and start plugging things in here. So using this information here, I'm going to start by converting this 99 grams of glycine into, we'll just write C2H5NO2. We're going to convert that into moles of glycine. 1 mole is 75.07 grams. And then that is going to be equal to, let me just find all my numbers over here, 1.31877 moles of glycine, C2H5NO2. And then now, since I have the moles of the solute, then I can use this equation to figure out what the molality is by just dividing this number by the kilograms of solvent. So that's going to be 1.31877 moles of solute divided by 1.2 kilograms of X. And so let's put in some labels here. So this is going to give me my molality for this solution that I've created, right? So then that value is equal to 1.09897 molal. So that is going to be what would go into our equation up here. So just be very careful. I'm carrying a lot of sig figs here because we're doing this equation work. I want to carry that to the end and then round at the very end of that process. Now I can plug the information in up here. So delta TF we know is 7.3. Again, that's coming from here. The temperature is lowered by 7.3 degrees. That is going to be equal to KF, which is our unknown. We do not know, in here, we're not told what mystery liquid X is. We're not told what our KF value is. So, that's what we're solving for. I'm going to use this molality that I just solved for, 1.09897. And then, like I said earlier, the Van Hoff factor for this first one using glycine is going to be 1. And I know that, again, because it's a non-metal, it's a molecular compound. When we dissolve it, it's not going to break up into multiple pieces. So we'll go ahead and solve for KF here. And KF for our unknown solvent X is 6.64. So that's going to be what we're going to use then to solve for the second part and ultimately, figure out what we're looking for here. So I'm going to move over here. Sorry about this indent. And we're going to basically apply this equation again. Delta TF equals KF times molality times I. We know now what our KF is, right? We've solved for that here, 6.64, so we can go and plug that in. And then let's sort of figure out what the other information is. So it says, on the other hand, when 99 grams of ammonium chloride, so we can see that we can solve for the number of moles of ammonium chloride, are dissolved in the same mass of X, which is this 1,200 grams. So I'm seeing that we can solve for our molality for the second solution. The freezing point of the solution is 17.4 degrees Celsius lower than the freezing point of pure X. So that tells me that this delta TF is 17.4. Now we need to figure out what the molality is, right? So maybe I'll solve for that molality. Actually, let's just do it up here. So we're going to take this information, 99.0 grams of NH4Cl times 1 mole over 53.49 grams. That's going to be 1.8508 moles of NH4Cl. And then we would divide that by that same 1.2 kilograms of our solvent X, because again, it's telling us it's dissolved in the same mass. And that's going to give us our molality for this other solution. And that equals 1.5423 molal. So that is the molality when we create the same solution with ammonium chloride. And I can plug that in down here, 1.5423 molal. And then our only unknown now becomes this Van Hoff factor I. We can go ahead and solve for that. And we'll see that I is equal to 1.699. And then now is when we would want to sort of think about, let's round that to the proper number of sig figs. And since our delta TF, so sort of we have to sort of look back and figure out, where we want to go with this. So our K, if we think about our KF value here that we calculated, this value here should actually only have 2 sig figs because our temperature here of 7.3 only has 2 sig figs. So our final answer should also have 2 sig figs. 1.7 is our final answer. So really, if we want to sort of be totally correct here, this KF that we calculated should only have 2 sig figs. Since we're doing all of these calculations together, I brought it over. It's probably fine. Obviously, it's fine. But then we do want to sort of make sure at the very end, how many sig figs should we have? Or maybe your professor is nice and tells you the number of sig figs. That is an option that they can do, but this is how we would get to this answer. So then let's talk about real quick, what does this mean, right? This I value of 1.7, that means that for every 1 ammonium chloride that you put in there, it's essentially breaking into 1.7 pieces. So that's where we get in the concept of partial dissociation. It's not completely dissociating. Obviously, this is experimentally determined, but that's sort of how that works. So I'm actually going to pause this video here or end this video. I'll do another video for the next example, which is slightly different. So there'll be 2 parts to this. All right, thanks a lot.